In our project, we are aiming to solve polluted runoffs from agricultural land and potential organic pollution, mainly to prevent the eutrophication phenomenon and any chemical contamination from agricultural practices. This includes, but is not limited to, algae growth, pesticide runoff, overuse of fertilizers, bacterial and other potential sources of pollution. Our system begins with a computer-based water analysis system, which has been proved to be effective in many industries. All the data will be passed to a core part photocatalyst water treatment system. It is a relatively new technology that can disintegrate unwanted ingredients. Different from many commercial systems, we will use a combination of varying photocatalysts and other materials for the best outcome.
For the stakeholder, the system can definitely have a positive impact on the individuals, governments, and institutions involved with water. The residents as a key stakeholder would be first affected by this system. They can enjoy pure water in nearby places rather than pollution water from agriculture. And some businesses and public facilities can guarantee their products and services are involved with water. The government administrations and administrations, as well as water regulation agencies, can well detect and manage water quality to keep their people safe. Additionally, the system needs a lot of local workforces to make more employees, but some occupations related to water detection, like water quality inspector, may be faced with unemployment.
Conceptual model is merely aimed at the process of data collection, processing, and the promotion of system algorithms. We will design and develop a software for PC ports that will collect and store the data returned by the installed pollution detection equipment. This system is mainly to deal with the increasing and difficult water pollution problems caused by the agricultural discharge, and finally achieve the purpose of improving water quality. After forming an algorithm through data accumulation, the system will automatically identify the degree of water pollution and enter the purification process. At the same time, the system will continue to track and collect water purification effect data and constantly reverse the algorithm based on this returned data. The interaction paradigm will be ubiquitous computing, and the interaction model will be manipulating. And also, we can see there are three potential metaphors.
Photocatalysis is a treatment mechanism that is generally more suitable for smaller bodies of water, as the process involves water passing through tubes or pipes that have a catalyst in them. So the biggest question we need to tackle is, how do we implement this for larger bodies of water? Another question is, as additional features or as a substitution to implementing treatment of larger bodies of water, can we use photocatalysis to obtain drinkable water from these larger bodies? If so, what kind of measures need to be added to detect whether the water is purified enough to drink? An area that requires further investigation is the workaround for turbidity. Turbidity is caused when insoluble particles present in the water, and it limits the performance of photocatalysis. Whether we use a filter externally, fitted to each device, or something else that needs to be added internally is yet to be figured out. Whether each device will have an artificial UV light system attached to it, or only the ones placed in locations with low sunlight accessibility, is a question that's yet to be answered as well, because it depends on a major cost factor. The current prototype is a low-fidelity sketch which primarily follows the path that the water must take, as well as the points at which the model will be applied and the data will be collected. In this prototype, we can see that there are 5 steps to this process to efficiently convert contaminated runoff into clean water that is safe for the environment. The first step of this process is that the runoff will flow to a low point of the land, being a gully or a stream. At this point, we would be collecting data based on the pesticides and chemicals used in that agricultural practice. In the next step, we will collect data about the flow of water before and after the contaminants have entered the stream. The next step would be to apply it to the models that have been developed over a testing period. These models would include output variables that include intensity of the UV light, catalyst for the runoff, any filtration that might be required before or after, and the desired quality of the water. Step 4 is when we use the data in the model to apply the photocatalyst system and do the physical cleaning of the water. With this step complete, we analyse the water quality one last time to get an output result, and finally release the water into a larger body. Questions identified previously will require further investigation and research into the area and use of devices for different problems identified. For example, use of photocatalysts for larger volumes of water, as well as probability of obtaining drinking water. If so, this might require further implementation of devices to ensure that the water is pure enough to drink. As far as turbidity is concerned, implementation of any devices, internally or externally, like filters, might help, and further research would make it more clear. Collection and storing of data will help in tracking and recording the quality of the water after purification, Depending on the pollution, the appropriate chemicals are released for photocatalysts, and the data is analysed after purification of the water and recorded in the system's algorithm. Further investigation and research will be conducted to find the solutions to the questions and doubts raised based on the current information, and it will definitely require further iteration into the concepts of photocatalysts.